Good evening, this is Mr. Murray, and we're going to have a video on transformations. We've been doing a lot with graphs, and the next step is not very difficult. It's just to move the graphs around based on some transformations. And this page has a lot of definitions that I'd like you to know. I'd like you to hear these words and understand what they mean. So perhaps dilation, to stretch or widen. You might think of that as when your eyes are dilated. And when you flash a light into them, they turn your pupils turn very small. And, when you take the light away, your pupils dilate. They become bigger.
Does anybody want to buy my shirt?
But these are very important. Nothing earth-shattering for sure. But, before I was teaching this course, I wouldn't think displacement meant up or down, so please just get used to some of these words and what they actually mean. After that, it's pretty straightforward. I'd like you to put these in your calculator. So I've done that ahead of time. I'll show you what mine looks like. I took this x squared as my parent function, and I want to see what happens like, what if you do x squared minus 5? What if you do x minus 2 in parentheses and square that? Compare that to x squared. So look at what I have in my calculator, and I'll address them one at a time. So I've got this list. I put x squared as my y1, so I would suggest you do that. And then x squared minus 5, x squared plus 4, x minus 2, all in parentheses, squared. X plus 7 in parentheses, squared. These are transformations. Let's see what happens when we do that. So take a moment to get those loaded in. And what I'll do is I'll graph x squared by having the equal sign highlighted. And then I'll go down to maybe, x squared minus 5. Highlight that equal sign, so that when I hit graph, both of those will be graphed at the same time. And that's how we can do a little comparison, okay? So looking back at your notes, we have x squared as a parent function, and let's see what happens if you take your x squared and start adding stuff to it. What will it look like? All right, let's go. All right, that's x squared, right? Let's add in the next component. Maybe I can even change the color or something funky like that. Let's see what we got. No, I can't. No good. Well, I can make it a fatter line. Let's see if that works. Nope. Oh, because I have to hit enter. Sorry. Okay. Wow, look at that. Awesome. Okay, so x squared is that guy who's hanging out on the origin, but then all of a sudden, boom, it drops down 1, 2, 3, 4, 5. So it's the same graph, but we just lowered it, right? Take a look at our notes. I think that makes sense. And we'll find out why in 1 second. All right, let's go to B. What happens if you do plus 4? Go to your calculator. Y equals. Let's get rid of that guy. And let's activate this one. Let's change the graph so it's a little more noticeable. Okay, perfect. What do we have? X squared. Whoa, where'd it go? It's up 4. It's the same graph, right? Up 4. Go back to your notes. Sorry. Whoa, hello. There we are. That was plus 4. Okay, so I think what you notice here is when it was minus 5 after the function, it went down 5. And when it was plus 4 after the x squared business, it went up 4. Very cool. Now let's take a look at what happens with these guys. If you're going to give me like a negative 2 inside the parentheses and then square it, remember the original looked like this. So if you're going to introduce something inside that parentheses, what will that do to the graph? Let's take a look. I'm going to get rid of this one, and I'm going to turn this one on. X minus 2. I'm going to hit enter to turn on that graph. Change it so it's a little more visible to you. I'll make that a fatter line, and let's see what the graph is. There's x squared. Whoa. You know what? The fatter line doesn't look so nice. Let me change it to something else. It sort of overlays what I want to show you. No. Nope. Bouncing ball, what does that do? X squared. Ah, check that out. Isn't that awesome? That's so cool. That's pretty slow, but anyway, it's working. All right, so can you imagine, if it's not that clear, I apologize, but you know, it took this parabola and moved it over like 3 times, or 3 units, didn't it? Or was it 2? Let me check my notes. All right, it was 2. All right, so we took our parabola like this, right? And it looks like we moved it over twice. Now, spoiler alert, this +7, I guarantee you, is going to look like we moved it to the left to number 7. And let's just verify that. Y equals, let me go down. I'm going to get rid of that guy, graph it. Let's see what it looks like. There's x squared. Whoa, wouldn't you know it? There's my parabola now moved over 1, 2, 3, 4, 5, 6, 7 to the left. And if you look at your notes, it certainly says +7, doesn't it? So what we have here is this kind of curious thing that when you transform a function and you do it with a +7 inside the parentheses, it's actually going to move to the left 7 units. And if you do a -2 in the parentheses, it will move to the right 2 units. Not so bad, right? So, I mean, to tell you the truth, this is about 80% of it. This stuff here. Give me a number outside of everything, it'll do exactly what you say. Down 5, up 4. Give me a number inside of everything, inside these parentheses, it'll go in the opposite direction, left and right. If you look at your definition sheet in the front, this is called vertical, and this is called horizontal. Remember, it's important to know these definitions. Okay, next. Let's do some combined transformations. So I hope you're at the point now where this is kind of easy, and you're going to say to yourself, all right, if I'm inside, I'm going to the opposite direction. So I'm probably going to go left 2. And if I'm outside of everything, I'm going to go down 3. This guy here, I'm going to go right 5, the opposite direction of the sign, and up 6. This isn't our normal parabola. That's why we have this example for you here. It's not centered at the origin. It's not a very perfect world. That's not what we're dealing with. We want you to get used to the fact that sometimes functions don't start off normal or nice. This function here is a little bit south and to the left. However, it can still be transformed. So if this is your given function right here, let's transform it according to this. So I'm going to take some key points, move them to the left 2 values. So this guy here is now here. This guy here is now here. This guy here is now here. Okay, that's that transformation. Now, -3 outside of everything says let's go down 3 units. So this point now needs to be moved down 3. And let's get rid of that so we don't get confused. This point here should go down 3, like that. And let's get rid of the old one so we don't get confused. Last but not least, this point here should go down 3 to there. And let's get rid of that guy. Okay, now what do we have? A new parabola that looks just like the old one, except it appears that it has gone to the left 2 units and down 3 units. It's as simple as that. Now I think you can imagine what would happen to this one. So let's not waste our time going over that. Let's move on to the next slide. Now, if someone verbally says, or in a word problem says, hey, listen, I've got this graph of x cubed. I want to go 5 to the left and down 7. What would it look like? Okay, well, that's easy for us now. Because if f of x is x cubed, our friend would have to be this. How do I go to the left 5? I put it inside the parentheses with a positive sign. How do I go down 7? I simply say minus 7. Now, if you don't believe me, you put this in your calculator and watch the magic. How about this one? What would produce the graph of a function g if I started out with the function f? Okay, function f, what are you? X squared. What does g want to be? X minus 1 squared plus 3. So describe the transformation. I think we can do that. We're going to say x squared moved left, or you want to be fancy schmancy, right? Horizontal, so we can get into the dinner party that we all want to go to. Left 1 unit and down. Was it down? Oh, no, it was up. Sorry, my bad. Sorry. Cool. Same color, yeah. Up, how many? 3. And of course, that's called vertical on the inner circles of these very fancy math people. Units. Okay, the handwriting is hideous. I'm sorry about that. But, you know, this question said, please describe. So here are some words that describe. And this one said, just give me the equation that results in this transformation. Here it is. There's one more thing we have to look at. It's called dilations. This is that, you know, your eyes are getting bigger kind of thing. So besides the in and the out and the stuff like that, what about a multiplier? Not a minus 7, but like a times 3. And what's the difference if it's in the parentheses or just multiplied against it? What kind of effect does that have? Well, let's go to our calculator and graph them. You know what x squared looks like. Let's not kid ourselves. It's like this, right? That's easy. But what's this going to look like? What happens to our graph? I'll tell you right now, it doesn't move, but something curious does occur. And the same thing here. What happens with this multiplier in the parentheses versus this multiplier just next to it? 3x squared. Let's compare the graphs. There's x squared. Ooh, there's 3x squared. Very cool. What I'll tell you happened is this. We took this graph of x squared, and when we multiplied it by 3, it's the same vertex, goes to the origin, but it's a little bit thinner. Now let's compare that to parentheses 3x all squared. And let's see what happens there. I'll go to my y equals, go down here, let's insert some parentheses. Okay, what does parentheses 3x all squared look like on a graph? There's x squared. Woo! It's actually pretty much thinner, but it's still the same graph. So let's go back to the notebook so I can show you. Okay, so this one here, that took x squared and actually did a little bit thinner than this one did. And it kind of stretched it. Okay. So here are some definitions for you to look at. If you put a multiplier on the outside, it stretches it by a factor of n. And if you put a multiplier on the inside, it stretches it by a factor of 1 over n. So here's the idea. If you have, just in general, okay, if you have something like 3x squared or 3x all squared, your graph is going to start like this, and it's going to end up thinner. Now this one might be much more thinner than this, but it does stretch it and makes it closer to the y-axis. Now if you have a fraction on the outside, it makes it very wide, sort of like the vertex and directrix questions that we've always been working on. It's always been a wide parabola. So let's take x squared, and that would just look very much like this, right? Now, if you had, for example, 1/3 times x squared, woo, that turns into a salad bowl. It gets really, really wide. So that would be this guy. That's what this is saying down here. If you have a multiplier out front and it's a number bigger than 1, it's going to get very narrow. And if you have a multiplier out front that's a fraction, in other words, less than 1, but greater than -1, you have a very wide parabola. And those are the basic transformations. Now, what you see up here are the table of values. And that's what really builds a graph, right? So you can see the difference between these three examples, what the y values are. It gets very large here when you have a multiplier of 3. Every answer gets multiplied by 3. But when you put the 3x in parentheses and then square it, it gets larger even faster. This is very explosive. So by using these multipliers in different forms, you go from 4 to 12 to 36, 1 to 3 to 9, and so on. And what that does is it just speeds up your graph and gives it the appearance of being closer to the y-axis, or as if someone's pulling up the parabola over here by these shoelaces. You know, if you pick them up, you would thin them out. If you have a fraction, you push them down, which actually widens them. Those are transformations. Those are the basic ones we need to know. And tomorrow you'll have a worksheet where you can practice all of this. I hope this video was helpful. Zanfini and I will see you tomorrow morning. Have a great evening. Take care.